Hello everyone. Today we are going to talk about representations of graphs which are popularly used to represent graphs in computer's memory. So basically there are two kinds of ways which are used. First one is with the help of linked list, that is the collection of adjacency lists. We have to maintain a linked list corresponding to each and every vertex present in the graph. The second representation that is used, it is based on the concept of arrays and it is known as adjacency matrix. We have to maintain a matrix in order to represent the graph. Both the ways, they are equally applicable to represent a directed as well as an undirected graph. However, if we talk about the preference, then if we are working with sparse graphs, that means the number of edges which are present in a graph, they are very less as compared to the square of the number of vertices in the graph, then adjacency list representation is preferred. On the other hand, if we are working with a dense graph, that is the number of edges which are present in a graph, they are approximately equal to the square of the number of vertices in the graph. In other words, we can say a dense graph is a graph in which edge is existing between almost every possible pair of vertices. So if we are working with such a graph, then adjacency matrix representation is preferred. However, both the representations, they have their own advantages as well as disadvantages. So when we have to work with the graphs, at that time we have to pick either of the two ways in order to start. And the decision, it depends upon several things like the platform which we are using, the demand of the application, the prominent operations of graphs which are needed by that application, and so on. So depending upon the requirement, we have to decide either of the two ways to choose. So now we will look at both the representations. We will discuss few points with respect to both the representations and then we will switch to the examples. So starting with the adjacency matrix representation. So matrix, it is nothing but a two-dimensional matrix of size V cross V. That means the number of vertices cross number of vertices. So number of columns as well as number of rows in a matrix, it comes out to be total number of vertices present in the graph G. And when we are talking about the entry Aij, at that time we are looking at the edge in between the vertices I and J. So if we talk about an undirected graph, at that time, if an edge is existing between the pair of vertices I and J, we have to put 1, otherwise we have to put 0. If it is a weighted graph, then in place of 1, we have to put the weight. In a similar way, if we are working with directed graphs, at that time, we have to take care of directions of the edges in between the vertices I and J. So if an edge is existing between a pair of vertices I and J such that the edge, it starts from vertex I and ends at vertex J, then only we have to put 1, otherwise we have to put 0. Similarly, if we talk about a weighted directed graphs, then in place of 1 we have to put that weight value if the edge is existing between vertex I and vertex J. So based on this, when we work with the undirected graphs, then the adjacency matrix which is obtained, it is actually a symmetric matrix, and it is symmetric just because of the fact that Vij equals to Vji, which is nothing but the symmetric property that we have already studied during the undirected graphs introduction. That is, the pair of vertices, they are unordered when we work with undirected graphs. However, when we work with directed graphs, then the pair of vertices, they should be ordered based on the direction of the edges. So let's say here is a simple example. We are working with a graph with 4 vertices and 4 edges. So we have to simply create a matrix of 4 cross 4 because we have 4 vertices. So we have created this matrix and then corresponding to each edge I have to put one entry. So the edge is existing between pair 0 and 1. So we have 0, 1. And this entry, it is representing the edge and it is equals to 1. Then there is no edge in between 0 and 2. So you can observe for 0, 2, we have put 0. And then again there is an edge in between 0 and 3. So 0, 3, we have put 1 and so on. So in this way, we can generate a matrix representation for any graph. Similarly, if we talk about directed graphs, then before putting the one value, we have to look at the directions of the edges also. So here we have only two edges 0, 1, 0, 2 which are originating from vertex 0. So accordingly, if we look at the entry 0, 1, we have put 1. If we look 0, 2, then also we have put 1. But there is no edge which is existing like 2, 0. So if we look at 2, 0 entry, then it is equals to 0. On the other hand, if we look at this, then 0, 1 in edges existing, we have already seen that. And since it is undirected graphs, so this symmetry is maintained by putting 1 for the edge 1, 0 as well. Because 1, 0, 0, 1, they both are representing same edge in case of a undirected graph. Therefore, if you observe across this diagonal, then the matrix which we have obtained for the given graph, it is nothing but a symmetric matrix. So we all have studied about several ways one can use in order to represent the symmetric matrix efficiently in computer's memory. So you can use that way also. Otherwise, if I work with this simple representation, then the memory requirement to store a graph with the help of adjacency matrix, it comes out to be V square because we are generating the array of size V cross V. Similarly, if we look at these entries, then total number of non-zero entries will always be equal to twice the number of edges in the graph. You can count this thing. For example, here we have 4 edges, and if 4 edges are there, the matrix should have 8 non-zero entries. We have 1, 2, 3, 4, 5, 6, 7, 8. On the other hand, if we talk about a directed graph, then number of entries in a matrix, it should be equals to total number of edges in the graph. So we have 4 edges here, and you can see we have 4 non-zero entries present in this matrix. After that, the concept of degree comes. So if we take either row sum or column sum, in case of an undirected graph, then the number obtained, it will be nothing but the degree of that particular vertex. So this is true if we talk about the unweighted graphs. If it is a weighted graph, then we have to actually count at the total number of non-zero entries. So here, if we look at 0th row or 0th column, then there are 2 non-zero entries, and so if we sum up these values, we will get 2 also. Similarly, if we talk about a column, so here we have 2 non-zero entries. Also, if we sum up, we will get 2. So from row or from column, if I get the total number of non-zero entries count, then it will give me the degree of a vertex in the case of an undirected graph. On the other hand, if we work with the directed graphs, then if we look at the non-zero entries in a single row, then that will give us the out degree of a vertex. So here we have 2 non-zero entries, and since again it is an unweighted graph, we can sum up these entries also. So in both the ways, we are obtaining 2, and 2 is nothing but the out degree of vertex 0. Similarly, if we look at the column corresponding to vertex 0, then it is having only 0 entries. That means there is no edge which is coming into the vertex 0, and hence its in degree is 0. That means if we look at the column sum or non-zero entries which are present in the column corresponding to a vertex, then we will get the in degree of that vertex. So if we take an example of vertex 2, so row sum corresponding to vertex 2, it is having a single non-zero entry. So its out degree should be equals to 1. Similarly, if we talk about the column sum corresponding to vertex or non-zero entries in the column corresponding to vertex, then it is also 1. So we can say that the in degree of a vertex 2, it should be 1. So basically, once we have created the representation of a graph in the computer's memory, then we don't need this pictorial representation of graphs. We have to actually work with the matrix or with the list, whatever we have chosen. Next, if we have a weighted undirected graph, then again it is weighted. So instead of putting 1, we have to put the weight values, and also since it is undirected, so the matrix, it should be symmetric. Rest all the properties that we have considered corresponding to the degree, it will remain the same. We have to simply count the non-zero entries corresponding to each row or each column. Both will give us the degree of a vertex. Next representation, it is the adjacency list representation. So here we are going to make use of linked lists corresponding to each and every vertex. So what we need, we have to make use of an array of linked lists with size equals to b. So as I said, we have to maintain a linked list corresponding to each and every vertex in a graph. So in order to store the head pointers of all the linked lists, we should maintain an array. Although instead of array, you can work with the linked list also, but in this course we are assuming that the head pointers, they are maintained with the help of array. And then an ith entry of an array points to a linked list of vertices which are adjacent to vertex vi. So this gets clear when we look at the example. And similarly, if we are working with the weighted graphs, then we have to simply update the structure of a node in order to accommodate the weight value corresponding to the edge. So we will see these points in the examples. So let's say this is the graph and we have to represent it with the help of adjacency list. So first we have to count the number of vertices in the graph. So there are 5 vertices. So we will create an array of head pointers with size 5. So you can see we have an array of size 5 and they are maintaining nothing but the address of the first node in each of the 5 linked lists corresponding to each vertex present in the graph. So if we talk about vertex 0, so vertex 0, it is adjacent to vertex 1, 2, 3, 4. So the linked lists corresponding to vertex 0, it will have all the nodes which are adjacent to it. So here 0 is adjacent to all the other vertices. So the linked list, it is having all the 4 nodes. If we talk about vertex 1, then 1 is adjacent only to 2 vertices, that is 0 and 3. So the linked list corresponding to vertex 1, it will have only 2 nodes. First one is 0th vertex and second is corresponding to 3rd vertex, and so on. And we have to put the null as we used to put in simple linked lists. So this is about the undirected graphs. So again, a few of the observations are, since it is undirected, symmetry is maintained. Because of that symmetry, the total number of nodes which are present in the linked list representation of an undirected graph, it comes out to be twice the number of edges. So if we count the total number of edges in this undirected graph, it comes out to be 1, 2, 3, 4, 5, 6, 7 and 8. So if we count, we have 4, 5, 6, 6 plus 3, 9, 9 plus 4, 13, 14, 15, 16. So 16 nodes are there. So whatever be the number of edges, the number of nodes in this adjacency list representation, it comes out to be twice the number of edges. Similarly, if we talk about the memory requirement of this representation, then we have just seen that it needs twice the number of edges as the number of nodes. Plus, we have to maintain this array for each and every vertex. So overall memory requirement, it comes out to be V plus 2 times of E. Since 2, it is a constant, so we will discard it. So memory requirement, it comes out to be V plus E. On the other hand, when we had studied the matrix representation, at that time the memory requirement, it comes out to be V cross V, V square. And here the memory requirement is V plus E. Similarly, if we have to work with the directed graphs, then we have to take care of directions. We are maintaining head pointers corresponding to each of the 5 vertices. And then if we look at any vertex, its list will have all the nodes which are adjacent to it. So 1, it is adjacent to 2, 3 and 4. So we have 2, 3 and 4. 5, it is adjacent to only single node, that is 2. So 5 is adjacent to 2. If we look at 2, then 2 is adjacent to only single node 3 because it is bidirectional. So corresponding to 2, we have single node 3. and so on. So in this way, if we work with the directed graphs, then total number of nodes which are used in adjacency list representation, it comes out to be total number of edges in the graph. So here we have 1, 2, 3, 4, 5, 6, 7 edges are there in the graph. So 7 nodes should be there. So these are the 4 nodes, 5, 6, 7. So 7 nodes are there. So again, if we look at the memory requirement, then we have total number of nodes equals to number of edges, and we have to maintain these corresponding to each and every vertex. So again, the memory requirement, it comes out to be order of V plus E. And then as far as the degree of a node is concerned, then we can compute it with the help of linked list representation also. So if I have to compute the degree of 0, I have to simply count the total number of nodes in the linked list corresponding to vertex 0. So I'll get 1, 2, 3, 4. Here we will get 1, 2, 3, 4. Similarly, if I talk about the degree of vertex 4, it should be 3. So we will have 3 nodes corresponding to vertex 4. So in this way, I can compute the degree of any vertex present in a graph. Similarly, when we work with the directed graphs, we have a concept of in degree and out degree. If we count the total number of nodes present in a linked list corresponding to a vertex, then that count will give us the out degree of a node. So here, out degree of 2, it is only 1, and we have only single node in the linked list for 2. Similarly, out degree of 1, it should be 3. There should be 3 nodes present in the linked list corresponding to vertex 1. So there are 3 nodes which are present. So in order to get the out degree, we have to simply count the total number of nodes in the linked list corresponding to that vertex. Then in order to get the in degree, we have to search for that particular node in the linked list of all the vertices. So if we talk about the in degree corresponding to vertex 2, what we have to do, we have to scan all the linked lists of all the vertices and count how many times 2 is appearing. So here 2 is appearing first time, then we will scan the second list, third list, we will obtain 2 again. So the count, it gets increased by 1, and then we will again scan the linked list corresponding to vertex 5, we will get 2 again. So again we have to increase the count by 1. So final value of the count, it comes out to be 3. And we can verify this thing from the in degree as is shown in this graph, that the in degree of 2 is 3. So this is all about the unweighted graphs. We have represented unweighted graphs with the help of a adjacency linked list. On the other hand, if we are working with the weighted graphs, so everything will remain the same, but we have to update the structure of a node. Previously, we are maintaining only the vertex number corresponding to the node entry for each and every linked list node, but now in addition to the vertex value, we have to maintain the weight also. So here, if I look at the vertex 0, then we have an edge from 0 to 1 and its weight is 0.2. So we have a node with value 1, that is the vertex 1, and the weight value, it comes out to be 0.2. Similarly, we have another edge from 0 to 2. So we have another node with value 2, which is nothing but the vertex. And then we have 0.4, which is the weight corresponding to that edge. On the other hand, initially we were simply maintaining only the name of the vertex in these nodes. So this is all about both the representations. And next we will take an example and try to construct the adjacency matrix as well as adjacency lists representations for the graphs, and the 4 graphs which we are going to consider are weighted graphs, directed as well as undirected, plus we will take simple graphs, directed as well as undirected. So we will discuss 4 examples now. Starting with the unweighted undirected graphs. So as we can see, there are 5 vertices in this graph. So we have taken an adjacency matrix of 5 cross 5 corresponding to each vertex present in the graph. So we will start with vertex V0. It is connected with vertices V1 and V2. So we have to put V0, V1. This entry should be equals to 1. Similarly, V0 is connected to V2. So this entry, it should be equal to 1. So we will put these two ones. Then V1, it is connected to V0, V2 and V3. So V1, it is connected to V0, V2 and V3. So we will put 3, 1 here. Then V2, it is connected to 3 vertices again, V0, V1 and V4. So we will put the corresponding entries as 1, V0, V1 and V4. And we have to repeat this process for each and every vertex. Now V3, it is connected to V1 and V4. So V3, it is connected to V1 and V4. And finally V4, it is connected to V2 and V3. So these are the entries which will remain 1. Rest all the other entries we have to put 0 because these edges, they are not present in the graph. So with this we have completed the adjacency matrix construction for the given graph. Now in order to construct a adjacency list representation for the given graph, we have to first define the structure. So we are familiar with this structure. We have to just create an array of head pointers in order to store the address of the starting nodes of all the linked lists corresponding to the 5 vertices. So the moment we declare this structure in the head 5 array of pointers, we will get something like this. Now again we have to create the linked list corresponding to all the 5 vertices. Since 0, it is connected to V1 and V2. So linked list corresponding to vertex 0 will have 2 nodes. First will be the node 1 and second will be the node 2 and then null. Same we used to do in case of singly linked list. Then for vertex V1, it is connected to 0, 2 and 3. So accordingly, we will have 3 nodes 0, 2 and 3. Then vertex 2, it is connected to 0, 1 and 4. So we have 0, 1 and 4. Then vertex 3, it is connected to 1 and 4. So here we have only 2 nodes, one for vertex 1 and another for vertex 4. And lastly, vertex 4, it is connected to 2 vertices 2 and 3. So we have 2 nodes 2 and 3 and that's it. With this we have completed the adjacency list construction for the given graph. And this process we have to repeat this process for each and every graph. So next graph we are going to talk about is the directed graph, but it is unweighted again. So we have to put 1 in the adjacency matrix. So again it is having 5 vertices. We will create a matrix 5 cross 5 and then before putting 1 we have to make sure of the proper direction. So here we have an edge from V0 to V1 as well as V0 to V2. So accordingly, corresponding to row V0, we have to put 1 for the column V1 as well as for the column V2. So we will have 2 1s. Similarly, V1, it is connected only to V3. Or in other words, what we can say, V1 is adjacent to V3 only. So we have to put single 1 in the row corresponding to V1 and column V3. Then we have V2. It is again adjacent to single vertex V1. So V2, V1, this column, it should have 1. Then V3, it is connected to only V4. So accordingly, we will have single 1 over here. And then V4, again it is adjacent only to vertex V2. So we will have 1 here. Rest all the entries, they will be equals to 0 again. So with this, we have completed the matrix for the given graph. Again, since it is unweighted, the structure will remain same. We have to declare the array of head pointers. So we are done with this. Now we have to generate the linked list corresponding to each vertex. So again, V0, it is having 2 adjacent vertices V1 and V2. So we will have 2 nodes in the linked list corresponding to vertex V0. Then V1, it is adjacent to single node V3. So V1, the linked list corresponding to first vertex, it will have a single node 3. Then V2, it is adjacent only to V1. So again, single node with value 1. Vertex V3, it is adjacent to only V4. So we will have 4 in the linked list corresponding to node 3. And then vertex V4, it is adjacent to vertex V2. So we will have a node with value 2, which represents that the vertex 4, it is adjacent to single node 2. So this completes the construction of adjacency list for the given directed unweighted graph. Now here we have an undirected graph, but it is weighted. Since it is weighted, we have to put weight values in the adjacency matrix instead of 1. Rest of the process, it remains same. So V0, again it is adjacent to V1 and V2 with the corresponding weight values 2 and 3. So in the column corresponding to V1, we have to put 2, and in the column corresponding to vertex V2, we have to put 3 for the row corresponding to vertex V0. So we will have 2 and 3. Then V1, it is connected to V0 via weight 2. It is connected to V2 via weight 5 and it is connected to V3 as well via weight value 2. So we will have 2, 5, 2 in the columns corresponding to the adjacent vertices. Then V2, it is adjacent to V0, V1 and V4 with weight values 3, 5, 3. So we will have something like this for the row corresponding to V2, and then we have V3 which is connected to V1 and V4 via weight values 2 and 9. So 2 in the column for vertex V1 and 9 in the column for vertex V4. And then lastly V4, it is connected to V3 and V2 via weight values 9 and 3. So we will have 3 and 9 here. So these are the weight values. Rest all the values we have to put 0. That's it. Now when we talk about the adjacency list representation for the given graph, then in addition to the vertex number, we have to store the weight value also. So all the things, they will remain same, but we have to make use of another variable in order to store the weight of an edge. So again, we have an array of head pointers, and now for vertex 0, the linked list, it will have two nodes, one corresponding to vertex V1 and weight value 2, and another one corresponding to vertex V2 and weight value 3. So we will have 1, 2 in the first node, that is vertex 1. It is adjacent to vertex 0 and the weight of the edge is 2. Similarly, vertex 2, it is adjacent to vertex 0 and its weight value is 3. Then vertex 1, it is connected to V0, V2 and V3. So we will have 3 nodes and the values of those nodes are 0, 2, 2, 5, 3, 2. We have 0, 2, 2, 5, 3, 2. Similarly, for vertex V2, we will have 0, 3, 1, 5 and last node will have 4, 3. 0, 3, 1, 5, 4, 3. Then for vertex V3, we will have 1, 2 and 4, 9. And lastly, for vertex V4, we will have 2, 3 and 3, 9. So with this, we have completed the adjacency list representation for the weighted undirected graphs. And lastly, we have directed weighted graphs. So again, we have to put the weight values along with the directions. So V0, it is connected to V1 and V2 via weight values 2 and 3. So accordingly, we have to put in the row corresponding to vertex V0 and the column V1 and V2, 2 and 3. Next, we have vertex V1. V1 is connected to two vertices, that is V2 and V3 via weight values 5 and 2. So we will have 5 and 2. V2, it is connected only to vertex V1 and weight value is 5. Then V3, it is connected to V4 and weight value is 9. And then V4, it is connected to two vertices, V4, that is to itself, and V2 and weight values are 2 and 3. So 2 with respect to the column V4 and with respect to column V2, we will have V3. So rest all the entries, they should be 0. So that's all for the adjacency matrix for the given graph. Then again, as far as the adjacency list representation is concerned, we have to make use of same structure as we have just used for the undirected graphs. That is, we have to make a space for the weight corresponding to the edge. So next we have an array of head pointers. Vertex 0, it is connected to vertex 1 via weight value 2 and it is also connected to vertex 2 via weight value 3. And then vertex 1, it is connected to two vertices, vertex 2 with weight value 5 and vertex 3 with weight value 2. Then vertex 2, it is connected only to single vertex, that is V1 via weight 5, and then 3, it is connected to vertex V4 weight value 9 and V4, it is connected to itself. So we have 4, 2 and it is also connected to vertex 2 with a weight value of 3. So this is all about the representations which are used to store graphs in computer's memory. So what you have to do now, just understand how to represent a graph with the help of a matrix and with the help of a linked list. Once you understood the concept using pen and paper, you have to write a program such that you have to take the input from the user and then you have to store that input, that is the graph, with the help of matrix in one program, and in another program you have to store the adjacency list. After that, you have to provide the user with a menu in which there should be several options like what is the degree of a particular vertex, or how many edges are there in the graph, or what is the out degree of a vertex, what is the in degree of a vertex if we are working with directed graphs. Or you can also ask for a pair of vertices, and then you have to identify if those two vertices they are adjacent to each other or not. Or you can ask for a single vertex from the user, and then you have to list out all the vertices which are adjacent to it and stuff like that. So basically understand the things and then do implement it. Okay, that's it for today. Thank you.